Welcome to this lecture series in group theory. In this lecture, we'll prove the Sylow existence and counting theorems, and let us recall the relevant things. So in the last lecture, we prepared some material in order to prove the Sylow theorems. So let's get started. So if G is a finite group and P is a prime, then we can write the cardinality of G in this fashion: P to the A times M, where M is relatively prime to P. Of course, this has nothing to do with the group nature of G. It is just a number theoretic fact. If you have any natural number, you can write it like this with this property. So nothing happened so far, but we defined a Sylow p subgroup of G as any subgroup of G having size p to the A. So this p is what refers to the prime in question, and a subgroup of G is a Sylow p subgroup if its cardinality is the highest power of p that divides the cardinality of G. All right, and now we saw a lemma after this definition that if this is the collection of all the subsets of G of this size, then we can act on this fancy S by G by left multiplication. Basically, this is the action. You take any group element and any subset of size p to the A, just translate that thing by G. All right. Now, if we fix such a subset, then the orbit of that subset has a subgroup of G if and only if this happens, meaning the cardinality of the orbit is relatively prime to P. So this is something that we proved. And at the same time, if this has a subgroup, then this has only one subgroup, and the cardinality of this thing has size M. So we will need these facts. We also showed this, which is a purely number theoretic identity, that this binomial coefficient is congruent to M modulo P. So we will need all of this. And let us also recall one fact about center of a group. If we have a P group, so when we say a P group, what we mean is cardinality of G is some prime power, P to the K for some K. Then G has a non-trivial center, which is another way to write it is that this is the case. So we proved it using class equation, which was a consequence of the conjugation action of G on itself. And with these facts, let us now get started. So this is the Sylow counting theorem. This is called the Sylow counting theorem. So yeah, NPG is the number of Sylow p subgroups of G. And this fact is called the Sylow counting theorem. This fact that there is at least one Sylow p subgroup is called the Sylow existence theorem. But of course, the counting theorem is stronger than the existence theorem because this already tells you that this has a size at least one. So what we'll prove is just prove the counting theorem directly. And here is the proof. So start with the action of G on script S that we recalled. The action by left translation on the set of all the subsets of G of size p to the A. All right, so this partitions script S, there's this fancy S into orbits. And there are two types of orbits. Orbits whose size is relatively prime to P and orbits whose size is divisible by P. So let O1, O2 up to OR be orbits with size relatively prime to P or not divisible by P. It's the same thing because P is a prime. And be the orbits. And O1 prime, O2 prime, dot dot dot, OS prime be the orbits with size divisible by P. Okay, so we know that script S, the size of script S is the sum of the size of all the orbits. Why? Because the orbits partition the set, and yeah, we have used this kind of thing a lot of times. So now we pass modulo P. So this implies script S is congruent to this modulo p, right? Because all of this is divisible by p, so that goes away when we go modulo p. But what is script s? Script s is p to the a m, choose p to the a. So that is congruent to, let me write it in a shorter way, that modulo p. And now recall this identity. So that gives us m is congruent to that. But as we noted in the recall, that if you have an orbit whose size is relatively prime to p, then that orbit contains exactly one subgroup of the group G, and the size of the orbit is m. So here is the fact. This has a subgroup of G if and only if its cardinality is relatively prime to p, and in that case, this has exactly one subgroup of G, and its size is m. So all of these sizes are m. This is mr modulo p, right? Because all of these sizes are m. And by again the recall, what is r? R is nothing but the number of Sylow p subgroups of G. Because the orbits which contain a Sylow p subgroups are these ones. These do not contain any Sylow p subgroups because their cardinality is divisible by p. So only these ones contain Sylow p subgroups, and each one of them contains exactly one. So R is nothing but npg. So let me just write here npg. And finally, since m is relatively prime to p, we have 1 is congruent to npg modulo p, because relatively prime things cancel out. Right, so that's a very nice proof of a very difficult theorem. Wonderful. And now let us look at a consequence. So suppose we have a group G and P is a prime, and say cardinality G is of this form where m is relatively prime to P, the usual. Then G has a subgroup of size P to the I for each I in this range. The Sylow existence theorem says that you can take I is equal to A, but now we are saying more, that if you have some prime power which divides the cardinality of G, then you have a subgroup of that size. And this is a generalization of, you could think of it as a generalization of Cauchy's theorem. Cauchy's theorem said that if a prime P divides the size of a group, then the group has an element of order P. Here we are not talking about orders, but subgroups. But if you use Sylow's theorem, the above theorem just boils down to this lemma. So take a group and P be a prime, and assume G is a P group. Its size is P to the power A. Then we want to show that G has a subgroup of size P to the I for each I at most A. So from here to there, it's very easy, because to prove this, you first pass to a Sylow P subgroup of G. So one will get a subgroup of size P to the A, and then apply this lemma. So this lemma immediately leads to that. And let me do the proof of it, maybe not in full details, but sufficient amount of detail. So let me isolate the lemma here. This is the lemma, and I really need the orange line. So let me copy. I think this will do. All right, so this is our lemma that we want to see the proof of. So there are two cases. G is abelian or non-abelian. Let me do the non-abelian case. So first assume inductively. So this is the main step. Assume that A is smallest for which the lemma is false. Right? So assume the lemma is false. Then there is the smallest A for which the lemma is false, meaning there is a group. So let G be a group. G be a group with the size of the group P to the A. And it does not have subgroups of size P to the I for each I. and G defies the lemma is how I'm going to write it. Defies the lemma. Okay, so we have a smallest A for which you can find a group which defies the lemma, and let's fix such a group. There could be many such groups up to isomorphism, but let's fix one. And now there are two cases. G is either abelian or non-abelian, so let me do the non-abelian case. So assume G is non-abelian. Right, now since G is a P group, and clearly A has to be, no, it's fine. So since G is a non-trivial P group, because A is at least 1, so G is a non-trivial P group, and hence the center of G, as we recalled, is non-trivial. But at the same time, center is a proper subgroup because G is abelian. So it's a proper subset of G. All right. Now define H as, let me not write H, maybe let me write G bar as G mod ZG. Then G bar has size some, let's say center has size P to the K. So let's say mod ZG is P to the K, where K is strictly between, sorry, K is in this range. K has to be at least 1 because center is non-trivial, and it has to be less than A because it is a proper subgroup of G. So with that, the size of G bar is also a group. Center is a normal subgroup in the group, so G bar is also a group, and the size of this group is smaller than the size of G. It is this size, and therefore by the minimality of A, we see that this has subgroups of size p square p to the power A minus K. It has so each for each number in this list, this has G bar has a subgroup of this size. Okay, so let h1 h A minus K be subgroups of G such that hi mod, let me write J, hj mod ZG, subgroups of G containing ZG such that this has size P to the J. So let me explain. Every subgroup of the quotient group appears as the quotient of a subgroup of G which contains the normal subgroup ZG. Right? So if we have a group G and N is a normal subgroup, what are the subgroups of these? These are precisely the subgroups of G which contain N quotiented by N. So since G bar has subgroups of size p square we can write those subgroups, or we can find subgroups of G h1 up to h A minus K which contains ZG with this property, because this is a subgroup of G bar with size p to the J. So I hope that was clear. We are using what is called the fourth isomorphism theorem or the correspondence theorem. Okay, so what does that mean? This means that the size of Hj is p to the J plus K, because this is nothing but the size of Hj divided by the size of Zg. Right, so what we have shown so far is that G has subgroups of size p to the power K plus 1 p to the power A. So all of these sizes are available in G. But at the same time, since center of G is a group of size smaller than p to the A, and it is a P group, we can find subgroups of ZG which have size p square p to the K. But if you have subgroups of ZG of this size, all of those subgroups are also subgroups of G. So G has subgroups of these size. So the end result is that G has subgroups of size p square p to the K coming from the subgroups of the center, and it also has subgroups of size p to the K plus 1 p to the A by this argument, by the quotient group argument. So this contradicts the assumption that G defies the lemma, because G is not defying the lemma. We are able to construct subgroups of G of all the possible sizes. So this is for the non-abelian case. For the abelian case, this argument breaks down because Zg is the full group. So G bar would be the trivial group, and you won't be able to do anything. But the abelian case is easier because you just apply Cauchy's theorem. What you do is you, rather than quotienting by the center, you just take any element of order p. Since G is a p group, p in particular divides the cardinality of G, so there is an element of order p in G. So just quotient out by that element of that order, of element of order p. This way you get a smaller group, and you can repeat this reasoning. The point where abelianness helps is that any subgroup of an abelian group is a normal subgroup. So when you're quotienting out by an element of order p, you are obtaining a group. This argument cannot be used for the non-abelian case because element of order p may not generate a normal subgroup. So that's the problem. So anyway, so the two cases can be dealt differently. The non-abelian case can be dealt via the center, while the abelian case can be dealt via Cauchy's theorem. All right, but the reasoning is once you go modulo a normal subgroup of size greater than size at least p and strictly less than the size of G, then the rest of the proof is the same. So the center was used only because it is a normal subgroup. If there was some other way to find a non-trivial proper normal subgroup of G, we could just use that and the same argument would go through. Anyway, so let me not stay on it too much. With that, let me end this lecture, and I'll see you next time.